Hey everyone, today I'm walking through a reinforcement learning project I worked on. This was something that just crossed my mind, thought it would be worth exploring the idea to see if it meant anything or could go anywhere. Assuming a reinforcement learning agent only had access to our keyboard, like the set of actions it could do are the keys it can type on the keyboard, would it be able to pick up or learn a new language? Obviously there's certain constraints criteria I set. It would have to have a back and forth with an OpenAI model, for instance. That way we can actually evaluate there's something it can learn, there are patterns it can pick up on. Ideally, it was a conversational setting where it picks up on those patterns and then effectively it grows and executes into meaningful English. The genome model that I'm demoing right now was the very first version of it that I tried building. It had keyboard access. You'd start across generations and it would rate it based off of vocab score, grammar score, coherence score, and then the best models will move on. The issue that arises with genome models, genome being like evolutionary models, are that if we look under the hood, all they have is a list of probabilities of what character should appear next in the sequence. So effectively, they're not learning as a neural network would. A neural network would form patterns on, given a certain character, given a list of characters before that character, what is the probability that the next character would appear in a sequence? Transformers work as, given a list of tokens, what is the next token that would appear in that sequence? So really this was just operating off a fixed set of probabilities that it thought was the probability that a sequence of characters should be printed out in. And the best models that moved forward, there was really no hard-cut judging criteria that would allow it to improve. The only knowledge that it had was the score that we gave it as to whether it was doing a good or a bad job. It had its evaluation, so it really had no way to find genuine meaning through experimentation. I then moved on to a character neural network model. This was a similar story where it had to generate the next character. I also gave it some more knowledge. I gave it words that it found anytime it found a new word, right? Suppose it printed out a character like I by accident, out of random. It's now going to get added to the word vocabulary. And the next time it's going to be incentivized to use that word as a given bonus. There's a bonus every time you use that word. This model was typing things that were a little more meaningful. It learned an understanding of what, like typing Joel repeatedly, it's learned through some form of attention that is something meaningful that is giving it a good reward. So it's learning based off of that. But this was the character neural network model we were evaluating. I then took it further into the word neural network model. I wanted to stay true to the fact that this model from scratch was figuring out the English language. So I was like, hey, the character NN model is now capable of finding words, right? Even simple words it can find. How can we plug that into the word neural network model, which now predicts words based off previous words? Can we generate meaningful sentences from the words that our character generation model created? That idea didn't go very far because our word sample size was limited, right? So I ended up pivoting. I ended up giving it 10K of the most common words as a Google data set. And now it goes ahead and generates sentences, but the quality of the sentences are still not particularly good, right? It doesn't know what it's doing, just stringing together words. The GPT is responding and it's giving it a score, but it really just doesn't understand meaning about subject verb predicate structure of the sentence, doesn't understand capitalization structures, doesn't understand where punctuation should go, doesn't understand a conversational setting, right? It's really just stringing together random words that it now knows to generate output. And so this wasn't really anything that could be used as well. This kind of brings us over to our final model. As you can see here, we went back to a genome architecture. Genome being, you could see a list of models here being called elite. A list of models being called child models and then mutant models, right? The elite models are the best models from the previous generation that are being passed on. So we think those best models have a capability of being the best. The child models are hybrids, or the children of two parent models that did decently well, that we believe that the child of that could do even better. They both have good individual traits. Mutant models are experimental models that branch off from these other system models. They're experiments trying something new that could maybe click. This sums up the genetic reinforcement learning process. Again, giving it the same word bank, it now started generating more meaningful sentence structure. It understood over generations, right? You could see which phase we're in. Phase two, the patterns phase. Phase one was the structural phase, where it understood sentence structure, that the noun or the subject should go at the beginning, we have some kind of verb in between, and then we have a predicate sentence, right? Obviously, you could see that the predicates of these sentences are still entirely random. There's no logic behind it. But if we were to go to a list of sentences that it's generated so far, I'd say it's done a semi-decent job. This is over the course of a couple hours that I ran this. The idea is it is generating something that resembles, to some extent, a sentence. And the reason I think this is a very exciting space to explore is because generally when we're training a model, we give it a whole lot of neurons and create this very complex mathematical function for it to be able to talk like a human. In this case, we have demonstrated that we don't need that complexity. We can simply give a model a set of possible words for it to choose from. We can give it a reward function of when it's doing well. We can pick out the best models and move them forward across generations, and it will get closer to generating sentences that are somewhat meaningful. The structure of English is there, and it's a learned trait for these models. These models in the very first generation did not understand how it should even English, and now it is able to generate these sentences, which is incredible progress. If you scroll down here, you can see some of our best conversations, the domain mechanics, guaranteed, accessories, wires, where. It looks like it's trying to say something. It's not really saying much, but we went ahead and picked out these bigrams, generated bigrams, two words that go together in a sentence structure. Like private message is a word that would appear in a sentence, right? So it's formed those valid bigrams. It's found some valid trigrams as well. It learns off of these and then reuses them in future sentences because it realizes, hey, I did a good job generating that, right? When it does a good job, we direct it, hey, you're actually generating English that somewhat makes sense here. Obviously, the score is very variable, and I haven't seen meaningful generation to the extent where it can hold a back and forth conversation with GPT yet. But hopefully, future work is that we develop a conversational reinforcement learning agent where it slowly starts to pick up tendencies that maybe GPT has talked about and improves based off of that. So this is the premise of reinforcement learning English. I tried to get this deployed on Vercel, but had a few issues, so should hopefully get that up within a few days. But this was educational content. See you guys.